This is part 3. So we're going to do balance of reactions, but also there are six types. 6 types that we will care about. They are the same 6 types that you learned in Science 10, but I know Science 10 was either a long time ago or a bad day, so we're going to try to do all the different types of reactions, and so learning the types allows us to predict what we will make. So that will be the hard part about what we're doing here. So we're going to start with a few symbols. I'm going to write the date down. It is May 5. May 5. Okay, the types of reactions. The first type is the simplest type. It's a synthesis, or a formation reaction, or a making something. We take 2 things, A plus B makes A and B. Very exciting. So A plus a B makes an A and a B stuck together. It's very exciting. So these kinds of arrangements show that we're not actually changing what anything is, we're just changing the order and arrangement of them. We can't make or destroy elements. If we start with A and B, we can't make C a different element. That's not possible. We can't do that. So we basically take elements by themselves into a compound. All right. Now we will basically work with trying to figure out what my product is going to be for this particular one. We got to figure out, we know we're going to make aluminum fluoride, right? That's what we're going to make. We're going to make aluminum fluoride. But we have to balance the charges of aluminum fluoride. So what is Al's charge? I'm just going to write them on the side here out of the way. What does charge? It's a 3. So it's 3 plus charge on aluminum. What charge does fluorine have?
2.
No, 1. So it's a 1 minus charge. So how many of each am I going to need for my aluminum fluoride? So I need 1 aluminum, 3 fluorines. 3 fluorines for every 1 aluminum. So now I'm going to write that into the formula spot, and I'm going to give a little gap, because remember, we're going to balance it after. AlF3. So that's the compound itself, aluminum fluoride. That's what we're going to make. If we put aluminum and fluorine together, we get aluminum fluoride. And now we can do our balancing steps that we learned over the last few lessons. And so now we got to look at what we have pointed out here. I've got fluorine with a 2 and fluorine with a 3. So we get to use 2Z, 3Z. I just need an excuse to say that out loud. And we put the 3 in front of the 2. So I turn my pen back on. 3 and a 2. And see where we're at now. So fluorine got settled here. But now I have too many aluminums over here. So I'm going to have to put some aluminums over here. 2 aluminums there, and I think that covers the answer. All right, the next type is a decomposition. It's basically synthesis backwards. It's A and B goes to A and B. So it's basically just backwards backward synthesis. But we're going to assume all compounds break down completely. I think I spelled compounds wrong. Compounds break down completely. So all the way down. So we break everything apart. So as I have right here, I have my, quick, this is going to be your quick quiz here. What's this thing called? H3PO4. What's its name? It has a phosphate in it.
Trihydrogen phosphate?
It's not trihydrogen phosphate.
Phosphoric.
It's phosphoric acid. The H starts means it's an acid. And so a phosphate means an ic acid. This is phosphoric acid. So what we're going to do is we're going to break it down into each of the elements that we have here. We have 3 elements here. So we're going to break this down into H's. Now, we have to check for diatomics. It's the only one I'm going to make you check first. It's the diatomic one. Is H one of the diatomics? Does it come in pairs? Yes, H does come in pairs. So this is an H2 compound. Does phosphorus come in pairs? Not usually. It's not one of the pairs I've talked about. And then we also need to make it into oxygen. Does oxygen come in pairs? Yeah, oxygen comes in pairs. So we have to figure out how to balance this particular equation. We take our phosphoric acid, break it down completely into hydrogen, phosphorus, and oxygen individually. All right. Where shall we start? Okay, so first thing we got here, we're looking at a 3 and a 2. We see a 2Z, 3Z there. We got to start there. It's the only way to get rid of the 2 and the 3. They got to fight it out. So we're going to put the 2 here and a 3 here. So that's hydrogen covered. Now we can work with which one's next. Should I do the oxygen or the phosphorus first?
Phosphate.
I'm going to probably do the oxygen first. Why would I choose the oxygen first? Because it comes in pairs. It might be weirder. Phosphorus all by itself, any element that comes in singles and is all by itself, is easy to do last. You just need to count it up at the end. You don't have to worry about anything. So always do the more complicated things first. So we're going to do oxygen first. How many total oxygens are over here? How many are over here? Got a lot of circles going on here.
8.
It's 8 total. So there's 8 total. How many pairs do I need to get to a total of 8? 4 pairs. 4 pairs to get to 8. Now, how many total phosphoruses do I have? 2 phosphoruses, and we have finished this particular question. So now we've got 2 phosphoruses, 3 hydrogen gas molecules, and 4 oxygen gas molecules. Excellent. Let's do the next one, Mn, and we got, looks like a oxalate, an oxalate set here. So we're going to break this thing down into an Mn piece, plus a carbon piece, almost called a copper piece. It's a carbon piece and an O2 because it comes in pairs. All right. So no 2Z, 3Zs happening here, so we don't need to worry about that. So we should try the oxygens first. How many total oxygens do I have over on the starting bit?
8.
You got 8, so how many pairs? Same as it was before, it's 4. All right, so that's set. Now we can just count out what's the total number of carbons that we have.
4.
4 carbons. And how many manganeses? 1. All done. And I put 1 on all of them. I like to put the ones when I'm balancing because it shows I've finished. Moving right along. Third one, single replacements. This is the dancing one I like. It doesn't matter. It's a trade. Let's do a few things here. We're going to do wrong colors. A plus B and C makes B and A and C. It's very fancy. So it's element, spelling, element plus compound, and then element, new element, and compound. So this is found in ionic compounds. Which are metal, non-metal pairs. No, covalents don't do this particular kind of reaction. They don't do that. So covalent compounds don't do this kind of single replacement reaction. So there are 2 kinds. There are metal SRs and non-metal SR for single replacement. Now, the reason there are two different types is basically which one of them are alone, right? So whichever one is alone at the beginning is the same alone later. So if you have a metal all by itself at the beginning, you're going to get a metal all by itself at the end. If you start with a non-metal all by itself at the beginning, you get a non-metal all by itself at the end. All right. So what are we doing here? We got a calcium and a potassium chloride. So which one of these do I have two of? Is this going to be a metal one or a non-metal one?
Metal one.
This is metal. Why is it metal?
Because it's calcium.
Calcium is a metal. I know you hear calcium and you think milk and bones, but calcium by itself is just a metal. Calcium ions are found in milks and bones and these kinds of things. But calcium metal is definitely not. It's a metal, just like sodium and magnesium and all those other ones. It's just all the same. Okay, so what we're going to do here is we're going to put, the next thing is going to be, if it starts with a metal all by itself, what's the other metal in here? The potassium is the other metal. So it's going to be all by itself. And then we're going to put Ca with the Cl. All right? So that's basically the trade. The metal traded the chlorine. So one chloride turns into the other kind of chloride. So we have to be careful here because we've made an ionic compound. We know it's a calcium and a chlorine. Are they balanced as they're written? No. What do I need to do to fix that? Calcium is a what kind of ion?
2.
It's a 2.
Plus.
And Cl is a what kind of ion?
Negative.
It's a -1. So how many of each do I need? What do I need more of? More chlorine. Now it's balanced. So now we've got calcium chloride. Now that's balanced. Now we can go on to balancing the reaction as a whole. This looks reasonably easy. How are we going to balance this thing overall? Well, first I've got my odd pair, right? I've got my 1 chlorine here, 2 chlorines here, so I got to fix that. So we're going to fix that by putting this 2 here. And now my potassium is too many, so I got to put that there. And now we're covered with our potassium and our set. I think we're good here. Yeah, that covers it. All right, next one, we're going to do a non-metal oxide because we start with a non-metal chlorine at the beginning. So what should come out of the sodium and the bromine down here? Which one of these two is going to be all by itself?
Sodium.
No. It's the bromine. It's the other one. Why is the bromine going to be all by itself? How do we explain this? Because it's non-metal. We start with a non-metal. We're going to get a non-metal in our first single spot. So that's the pair that we're looking for. So we're going to get bromine all by itself. And then we're going to sodium and a chlorine there. Now, we got to check, is the sodium and the chlorine balanced appropriately? We've made a new ionic compound. We always have to check that it's balanced properly.
No, it's not.
It is balanced appropriately. Swinging and missing today. You're 50-50 off today. So sodium and chlorine are both 1s. So we got sodium here, and chlorine is still the -1. So sodium and chlorine are both -1s. They're a 1-to-1. They don't change. And now we have to do a little bit of balancing. It looks like we're going to have to 2 the sodiums here. We have to 2 those. Oops, wrong color. Same idea, wrong color. 2 there, 2 there. That should do it. Because now my sodiums are good. Each of the nonmetals are, they're both diatomic. All the halogens in their column, F, Cl, Br, and I. I mean, astatine is too, but you don't see that very often. They're all diatomics, they all say. Yeah, that's the single replacement story. All right, guys. Next type is a double replacement. This is, again, also ionic compounds. Covalent compounds don't really do this either. So double replacement is a metal-non-metal pair. It's also probably worth mentioning that when we're doing ionic compounds, metals are always first. It's always the plus, then the negative. It's never written backwards. So you can always tell which one's a metal, even if you've never noticed that metal before. The metal's first. Whichever one's first is that one. And so when I write my little code for double replacement, it is an A, B plus a C and D. And how I figure out what I'm going to make from this, it isn't just a random mix-up, is the ones that are first have to stay first because they're metals. So they always have to stay first. They don't change what they are. So if A was first in the first part, A has to be first in the second one. But just the same way is the second part of each of the compound also has to stay the second part of each compound. So what's the only other thing that's not B that could stick to A? D is the only thing that could also stick to it. So A is going to match with D here. And that leaves the only pair left. It has to start with C and end with B. Right? So the last compound is a C and a B because C is a metal and B is a non-metal because of the order I wrote them in at the beginning. So if you start it one way, this is the only way it has to be. So this allows us to do a lot more with our double replacements. So one of the analogies for double replacements is your dancing partners of changing, right? So basically you just switch the dancing partners and that's how you figure out what the new reaction is going to be. Because I've got 4 things in my first example of reactions. I've got magnesium, chlorine, potassium, and sulfates. So I know I have to have a magnesium that has to go first. And I'm going to leave a bunch of space here. And I know that I'm going to have a potassium also has to be first. Those are my 2 metals. Now, I have to basically just switch the non-metals that they're stuck with. Magnesium was stuck to chlorine at the beginning, so now it's going to get a sulfate attached to it. Potassium had a sulfate attached to it, so now it has to have a chlorine attached to it. So we're basically switching our pairs. So each of the pairs is switched. And now we have to do a quick double check to make sure each of those is right. So what charge does Mg have on it in the periodic table? Mg is 2. Mg is in the second column. Mg is a 2. What does a K have?
1.
K is a 1. What does Cl have?
-1.
1. What does sulfate, the set, have?
3 if I believe.
2. It's a 2.
Oh, it's the phosphate that has.
Phosphate has it.
Okay.
How do we figure it out? So S is in column 18, 2 away from the noble gases. That's why it has a 2. P for phosphate is 3 away from noble gases. That's why it has 3. So now we take a look at our new compounds. Is this compound balanced? Yeah, we got a 2 plus stuck to a 2 plus, a 1 stuck to a 1. Okay, so each of our compounds is now set. Now we look at the big numbers out front for balancing. Big numbers out front balancing. Magnesium's looking good. Sulfate's looking good. Looks like my chlorines and my potassiums are the only ones needing to be messed with. That looks like we're going to be done with this. 1, 1, 1, and just a 2 at the end. That's not bad. That worked out pretty well. Nice and easy. All right. Let's see if you guys can do this one. This one's going to be fun. So take a second and try to set up this one. Watch the charges. Okay, up next is neutralization. Neutralization is just a special double replacement. So neutralization is a double replacement. It's just unique. So it's acid plus base. Oh, lost the ability to spell. What happens when I put an acid in a base? No. You can't destroy things. It makes 2 new things. Yeah, it does make water. Salt is right. Salt is right. So you make a water and a salt, not table salt. Salt's the class of ionic compounds. So salts are just the whole class of ionic compounds that are solids. So H2SO4, what kind of acid is that? Sulfuric acid. And then I've got a potassium hydroxide as my base. So I basically can apply my double replacement rules to this. But I know one of them is going to be water. Actually, I want to change colors to keep it consistent here. But that's the right idea. We know it's going to be water. And the metal and the non-metal. What's the metal in this equation? Potassium is the metal. What is the non-metal? Sulfate, SO4. Now we've done both of these already. We know potassium's a 1 and a sulfate's a 2, so we can put a 2 on this particular sulfate, just like we did with our the hydrogens also, why there's 2 hydrogens there. So now that's our formula. Now we need to balance it properly. So balancing it properly, H's look bad. So we're going to need to do a little bit of fun here. We're going to need the potassiums to double, and so I need those to double. That should do it for these ones. So I've got my potassiums sorted here, and then I have 2 O's and an H, and then 2 O's and 4 H's. So remember, the tricky thing with this one is kind of like the organic ones. There's H's here and here. There's 2 H's here, 2 H's here. That makes the 4 H's here because they're in 2 different places. I've got 2 H's in the potassium hydroxide, 2 H's in the sulfuric acid. Now I've got 4 H's in the water. So they have to add up on both sides. It is trickier when they're in 2 different compounds. All right, same thing. This is pretty easy. We just put the base first. That's not that exciting. So calcium hydroxide and phosphoric acid. So we'll put those together. We know the first one, H2O, easy peasy. And then we just put metal, calcium, and phosphate. Now notice I'm putting a little space in here because I haven't balanced them yet. PO4. So I'm going to put brackets around this because I'm pretty sure I'm going to need some little numbers around it. What charge does a calcium have? Plus 2. And if we're uncurious, we can look here and say, oh, it's probably a 2 because there's 2 hydroxides stuck to it. So it's probably a 2. And I've got 3 hydrogens stuck to this phosphate. So it's probably a 3. So the best way to do this particular balancing is 2Z, 3Z. So the balancing of this one, I need 3 calciums for every 2 phosphates. So now we can look at the overall balancing, and we start with this ugly thing. This is decidedly the most complicated thing, so we're going to try to deal with this one first. Calcium's 3, got to put a 3 over here. Then we look at the phosphates over here, 2 whole phosphates over there, so I'm going to need at least 2 phosphates there. And then we'll look and see if we get what we have to do with the waters. So we got to look at how many total hydrogens do I have in the first thing? It's a lot, right? So look over here. How many total hydrogens? 1, 2, 6, right? 6. Well, sorry. 6 hydrogens here and 6 hydrogens here. So 12. So how many waters do I need? 6 waters. Yeah? 8 plus 6, 14. They're both 8 and 6s. 8, 6, 8, 6. Okay, boss. Oh, darn it. Well, this is a surprise jump here. I'll pause that video. That's going to look sucky later. Yeah, so I just wrote a whole bunch on this page. I don't know where I last left off. Anyways, we learned how to balance things last time. What should we start with? Which of those things should we start with? Start with carbon. Always start with carbon. And I also want to sneakily put them up above. I'm going to put 8 up here. Because sometimes I have to double these, right? Sometimes I have to double them. So I'm going to start with an 8 up there. How many hydrogens or how many waters should I make?
You should make it like 9.
I should need 9. Uh-oh. What's wrong?
9
Odd, bad. Because there's no other oxygens in there. Because 9 is an odd. Can't do pairs of odd numbers. We have to double everything. So let's double it all. Start with that one. Get this one to 16. Get this one to 18. And then we've got to go from here. So that was the reason why we make the little balancing above really quickly. To be like, oh, I'm not sure. Oh, I have to double it. All right, so let's double everything. What is my total number of oxygens? Oxygens over here. I've got 16 twice. So what's 2 16s makes me 32. And then 18 signals. What is 18 plus 32? 50. Fantastic. So how many pairs of oxygens do I need? 25 pairs. What? 25. So that's 25 of them. So it's a lot, right? This is gasoline. Right? This is octane burning. Right? It's gasoline, roughly. Now, actual car gasoline has a whole bunch of other junk in it, which is generally the problem. Because if it was pure octane, we would have no problem. But if not. Because pure octane would only make carbon dioxide and water. But engine exhaust is not just carbon dioxide and water. That would be too easy. It's got a whole bunch of other crap in it. Nitrates and sulfates and all sorts of other junk that you get from digging the oil out of the ground. Moving on to metals. So metals don't make carbon dioxide and water, do they? Because there's no carbon there. I put potassium and oxygen together. What do you think I should make? Oh, something. Something with K and O in it. I'll just put them both here a little bit separated because I got to balance them. Because potassium has a +1 charge, oxygen has a 2- charge. So how do I put those together? K with a 2 and then O. So I get a metal oxide here. How do I balance this thing?
Put it 2 on the O2 on the left side.
Got to put a 2. No.
Or hang on, no.
2 there.
On the K.
And then a 4 here and a 1 there. Before we go past this one, as I slide it up just a bit, this is also a synthesis. So as much as this is a combustion reaction, because I burned it, it's also a synthesis reaction. It's just a special kind of synthesis. So these are both syntheses and combustions. And just like the neutralization ones are also double replacements. They're just special double replacements. Right. I gave you a good chunk of things to practice. We'll stop there.